We are going to go on to chapter 9, talking about Big Bang thermal relic. Start with talking about the scale dependence of radiation temperature. Uh, the So we're going to talk about thermal history of the universe, and in particular, in the latter part of this lecture, we'll talk about primordial nucleosynthesis or Big Bang nucleosynthesis, and why light nuclear elements formed in the Big Bang. So we're going to talk about the aftermath of Big Hot Bang. Uh, so the universe began hot and dense during the epochs immediately after the Big Bang. The universe was, compared to the present epoch, much more compact, and the energy associated with radiation motion of matter was much larger. That would say the universe was much hotter. The space was filled with plasma, in which various particles could be in thermal equilibrium through high energy interactions. As the universe expanded, it also cooled. As the thermal energy lowered, particles and antiparticles either disappear through annihilation or combine into various composite particles, or decouple, that is, cease to interact with the rest of the plasma to become free particles. Consequently, there remain today different kinds of thermal relics left behind by the Big Hot Bang. Our approach to study the universe history is to start with some sort of initial state, which may be guessed based on our knowledge or speculation of particle physics. Then we can evolve this proposed universe forward in the hope of ending something like the observed universe today. We can speak of the early universe with any sort of confidence rests with the idea that universe passed through a series of equilibria. At such stage, its property were determined independent of the details of interaction by a few parameters such as temperature, density, pressure, etc. So we could talk about thermal radiation. First, we'll talk about the description of thermal radiation. Uh, in this, we could neglect the particle mass and the chemical potentials. They're all small compared to thermal uh, energy. Case B is the Boltzmann constant. The number density, which means the number per unit volume, the number density distribution with respect to energy is the n is the number density, and E is the energy squared to E, and there's this denominator e to the e kBt. It was energy over kb, kt rather, uh, plus minus 1. Okay. The minus sign is for the case of bosons like photons, and plus 1 is for fermions like electrons. The h bar c, remember, has dimension of energy times length, so they're cubed, so energy cubed and volume. Energy cubed is cancelled energy cubed here, so therefore the right side here has a dimension of 1 over the volume, which is number density. It's correct, it's 1 over the volume. G is the number of spin states. Particles mass and the spin have 2s plus 1 states. And for example, spin will have electron have 2 spin states. But G always equal to 2 for massless particles, whether spin 1 or spin 2. Spin 1 like photon or graviton, they all have spin 2 states. Anyway, more on this in the book in chapter 9. Now we can integrate to get the number density for boson fermions. It turns out because the sign difference here, you have the boson number density versus fermion factor 4 over 3. And the boson number density is 1.2 times G over pi squared KT HC. Again, you can check that it has the correct dimensions. Then if you put energy at the end, so you integrate, you get integral, just get energy energy density, energy per unit volume, and find that this formula give you proportional to t to the fourth power. Okay, so the energy density, which sometimes we write uh, uh, rho sub r c squared as if there's a mass density, but really just energy is a notation, and g star over 2 some constant times 8 to the fourth. The constant is called Stefan Boltzmann constant, and it can work out to be this, and g star is effective number of spin states, because this formula works for both uh, bosons and the fermions. For fermions, it's factor 378. Okay, and otherwise you add up all the spin states for bosons and fermions. Because, so this is the famous Stefan Boltzmann law. The energy density is proportional to the fourth power of temperature. Now, then we can also find the average energy. You take the energy density divided by the number density. So energy per unit volume, number per unit volume. So therefore, you get energy per particle per number. So that's the average. But boson turns out Fermi related by a factor 6 or 7. In particular, the photon average energy is 2.701 kT. So we're now going to talk about scale dependence of radiation temperature. So remember we talked about we expect the temperature to drop as the universe expands. So how precisely it drops is, remember we derived the scale dependence of radiation energy density. The radiation energy density scales like an 8 to the 4 inverse fourth power, one power to the energy scale, then the volume. So the energy density scales like uh, minus 4 power. Now, but Stefan Boson tells us the energy density scales the temperature of the force. So therefore, we say the temperature must scale like a to the 1 over a. Okay? It was temperature, radiant temperature scales like inverse of the scale. This expresses precisely in scaling terms our expectation the temperature high when the universe is compact and cools and expands. Now, since radiation energy, not energy, radiation energy goes like frequency or goes like 1 over wavelength, so therefore scales like 1 over a. So therefore E over T are scale invariant because both scales like 1 over a. So this is 1 over a, this is 1 over a. So the universe expands at temperature lows, but the form of the distribution, the radial distribution, this e to the E over kt, is unchanged. So, so even though the temperature may drop, but the distributions remain exact same. Here's an example, just to calculate the cosmic time at a given temperature. If you know the radiation temperature to be this, we'll find out what's the time since the T equals 0 Big Bang. We looked at the first Freeman equation. We claim that the second term can be ignored because in a radiation dominant universe, remember we said A goes like time to the T to the square root of time. So A dot goes T to the minus square root of time. So therefore A dot over A goes like 1 over time. So therefore, as for early universe, when T gets smaller, so this term is much bigger than the second, so we can ignore the second term. So therefore, the Freeman equation says that A dot over A scales like a 1 over time, and so therefore the radiation is equal to the square of A dot A scales like a 1 over time squared. But Stefan Boson says the energy density scales like temperature to the fourth power. So therefore, we expect the cosmic time. The time goes like temperature 1 over temperature squared, T to the temperature minus 2 power. We can work out the coefficient. It's worked out in the book, and an example 9.1. And to get to an easy to remember numerical relation, the time, the cosmic time in seconds, S stands for seconds, as equal 10 to the power 20 power 10 to the 20 over temperature, when the temperature expressed in terms of Kelvin squared. Okay, so this precise relation between cosmic time was radiation temperature. So, for example, the temperature we know from at Big Bang nucleosynthesis, the primordial nucleosynthesis, the time when the light nuclear element were formed, is about 10 billion degrees. So if this 10 billion squared, 10 to the 18th, so therefore we expect the cosmic time for at this Big Bang nucleosynthesis is about 100 seconds. So you remember this famous book by Weinberg called The First 3 Minutes. That's really talking about uh, uh, this period of time. So that's the end of the first part, lecture 25.